Hello, AP Stat students. Today is our second day of talking about experiments. Today we're going to talk about the principles of experimental design, go a little more in depth than yesterday. First, I'd like to go through a quick example of what we talked about yesterday and just review the terms. So we have drug X is a new medication designed to reduce fever. Drug X is being tested for effectiveness and side effects. The experiment enrolls 1,200 patients with high fever to test drug X. 600 men and 600 women will be with ages ranging from 18 to 70. There are three different dosages of the drug, 325 milligrams, 500 milligrams, and 650 milligrams. The primary outcome measure is the drop in body temperature 3 hours after taking the treatment, which is the yardstick by which to measure the success of drug X. So, you're going to give one of those doses of medicine to each subject when they have a fever, and then 3 hours later, they're going to take their temperature and see if it has dropped and how much it has dropped. So the subjects would be the 1,200 patients with high fevers. The response variable will be the body temperature 3 hours after treatment. So they'll take their temperature before they get the drug, they'll take it after, and they'll see what the change is. The factors for this problem is just drug X. That's the only treatment being used. But there are three levels of that treatment, the 325 milligrams, the 500, and the 650. So the treatments, we end up with 3. Okay, that's a pretty standard experiment. Obviously, they'll basically have 3 treatment groups. So at 1,200 people, that'd be 400 people in each group, probably. And we would randomly assign those. So we'll get to that. Experimental design principles. So this is kind of the new stuff. There are 3 things that every experiment needs to have: randomization, replication, and control. Okay, without those 3 things, you do not have a valid experiment. Okay, so we're going to go through those 3 parts, so those 3 design principles. The first is randomization, and what we want to do is randomly assign the subjects to the treatments. Okay, we don't want to choose ourselves and say, oh, I'll put this person here and this person here, because we may have biases. We might accidentally put all the healthy people in one group and all the sick people in another. Or people that look friendly in one group and unfriendly in another. Whenever we make the choices ourselves, we're always subject to our own biases. So what we want to do is randomly decide who goes into which group. Okay. We've talked about random selection before in surveys. Taking a simple random sample. This is similar to that, except we're going to call this random assignment, okay? Because in a survey situation, we have a whole population, and we just choose some of them to take the survey, and we hope that our sample represents the entire group we're choosing from. But in an experiment, we want to use all of the subjects in the experiment. So we're going to assign each subject into one of the groups, but we want to do that randomly, okay? So just remember, random selection in a survey allows us to get a representative sample of the population, meaning that the small sample we take, is actually just a mini version of the entire population. Random assignment in an experiment gives us treatment groups that are essentially similar by spreading out the confounding variables between the groups. Imagine, you've got a group of 100 people. Some have good diets, some don't. Some exercise, some don't. Some maybe smoke, some don't. Some may have a history of health problems and some don't. By randomly assigning all of your subjects into the different groups, what we should end up with is an equal number in each group that are smokers, an equal number in each group that have good diets, an equal number that have bad diets, etc. We want to spread out all those variables equally among all of our treatment groups so that essentially each treatment group looks the same. Then the only difference between the treatment groups should be the treatment they receive, not some underlying factor. And if that's the case, if the only difference between the groups is the treatments, then any differences we see in the groups at the end of the experiment are a direct result from the treatment they received and not some underlying factor. So random assignment is super important, okay? So in an experiment, we want the only differences between our treatment groups to be the treatments they received. Random assignment allows us to equally divide any other variables between our groups. For instance, there may be smokers among our subjects. Smoking can have an effect on the results of an experiment. If 25% of our subjects are smokers, then random assignment would get us groups with approximately 25% smokers in each group. We want the only thing determining the outcome of our experiment to be the treatment each group receives, not some underlying factor. So randomization, super important. Now, how would you randomly assign into treatment groups? Well, suppose you have 100 subjects for an experiment, and there are 2 treatments. Okay, so I need to divide them up into 2 groups. To use random assignment, we could number our subjects 001 to 100. Remember, each label needs to have the same number of digits. Then we would use a random number table or a random number generator to choose 50 unique numbers from our list of 100. Those 50 subjects will be placed into one treatment group and the remainder in the other. That's one way we could do it. Another way, or a second method, I could label these. A second method would be we could write all 100 subjects' names onto pieces of paper and place them in a big hat. Then we could randomly draw 50 names, placing them in one treatment group. The other 50 names would go into the other. Or a third option, and there's many options to do this, we could also flip a coin for each subject. Heads would assign the subject to treatment group 1 and tails to treatment 2. And we'd just keep flipping until we had 50 subjects in one of the groups. The remaining subjects we placed in the other group. So each of those methods, what they have in common is that we use something random. Like names out of a hat is random. Flipping a coin is random. Using a random number table is random. Okay? And that should guarantee us that we get our groups that are basically similar so that the only difference will be the treatments. A second fundamental part of an experiment is replication. And that means having an adequate number of subjects in each treatment group. Okay? In general, the more subjects in each treatment condition, the more reliable our results will be. The more people you have in the groups, the more we balance out all of those like hidden variables that people may have with, prior health conditions or smoking habits or exercise levels, all that kind of stuff. The more people, the more subjects in the groups, the more reliable our results will be. So usually you'd want to get as many subjects as possible. You may be limited by budget or availability of subjects, but you want to shoot for as many as possible. The third technique is called control, and that's an attempt to minimize outside variability. Okay, so like, for instance, it could be the comparison of 2 treatments, an old drug versus a new drug. Okay, so half your subjects would get the old drug, half would get the new. Then at the end of the study, you could compare how did the old drug do compared to the new drug. If you just took all your subjects and gave them the same treatment, we'd have nothing to compare it to. So in an experiment, we want to have a comparison we can make at the end. Some experiments need a control group like a placebo, where if we only have one drug, then we would split the subjects up into 2 groups. One group would get the drug, and the other group would get maybe a sugar pill. The idea being that we'd want everyone in the experiment to think they were getting the treatment. And we'll talk about the importance of that here in a little bit. But anyway, so we need a control group. Okay, it could be an old versus new drug, or it could be a placebo. So a control group is a group in the experiment that does not receive a treatment by the researchers, but they should receive something. And most of the time we use a placebo, which is a harmless pill, medicine, or procedure prescribed for psychological effect. Basically, it's human nature that if you give someone a sugar pill, but you tell them it's an actual medicine, maybe for a headache they were having, people think their headache should go away, and that can actually make their headache go away, even though the medicine itself was fake and harmless. So we want everybody to think that they took a medicine or taking a treatment, so that psychological effect happens across everybody in the experiment. Then the only difference would be whether you actually got the treatment or not. Okay, so that brings us to the placebo effect. That's the measurable, observable, or felt improvement in health not attributed to an actual treatment. So you can, Basically, it's like tricking your body into getting better, mind over matter. If you think you're supposed to get better, you often do. Okay, so we make everybody think they should be getting better, so that effect is the same across all the groups. And subjects typically feel better when given any kind of treatment. If you give one group a drug and not the other, the group who got the drug may feel better simply because they got any kind of treatment, and not necessarily because of the actual drug you gave them. So here is our experiment that we looked at earlier. It's the same setup in red. The control in this one, if you're doing the 3 drugs, we may also do a 4th group with a placebo. That way we know for sure that the 3 groups didn't just get better because they took a drug. We'd want a group that just thinks they took it but didn't actually take it. Randomization, we have that because we randomly assign the 1,200 subjects to the 4 treatment groups. That would be pretty easy to do. And replication, divided equally, each treatment group would have 300 subjects. That's a lot of subjects, so that's a good replication. So we could make that experiment we talked about earlier have all 3 principles of a good experiment. 2 other terms that go along with this are blind, and that's when the subjects do not know which treatment they have received, and of course we want that. The subjects, we really don't want them to know which one they're getting because, again, if they know they're getting the strongest medicine, they may get the best results because they think they should. Okay, so that's what blind means. And then double blind is when the subjects don't know, but the researchers don't know too. Oftentimes in a medical study, the researchers will be in contact with the patients that are in the study, and we don't want the researchers to necessarily treat the patients differently based on which medication or which treatment group they're in, because that could bias the results as well. So if the researcher is going to be directly involved with the subjects, we'd want them to be blind also. So when the researchers don't know and the subjects don't know, that's called double blind. Okay. And of course, somebody knows. They would, hire an outside company to handle, who gets what treatment, and then at the end of the study, the outside company would tell them, well, these are the people in this group, these are the people in this group. That way the researchers wouldn't know. Now, there are 3 types of experimental design that we're going to talk about in AP Statistics. One is the completely randomized design, and this is when we just basically take all of our subjects in one group So we'd have all of our subjects in one group, and then we would split them up randomly into the treatment groups. So I had 2 treatments in this case. Okay, so that's a completely randomized design. All the subjects in one group, and then we randomly divide them into 2. Now, our second type of design is called a randomized block design. And this is when we would divide subject into groups based on a variable which might affect the outcome. Then we randomly assign treatments to all the groups. So, let's say there were smokers in our subjects, and we knew that ahead of time, okay? We could just trust that randomly dividing up the subjects will split the smokers up equally into the 2 groups. But if we wanted to be 100% sure, what we would do is before the experiment, we would ask our subjects, are you smokers? Or maybe give them a blood test and test for nicotine. And then we would start the experiment in 2 groups, where one group would be the smokers, and the other group is the non-smokers. Then we would basically be doing 2 separate experiments, where we would divide up the smokers into 2 groups, treatment 1 and treatment 2, and we would divide the non-smokers into 2 groups, treatment 1, treatment 2. Then we would basically be running 2 experiments, one experiment on the smokers and one on the non-smokers. Then we would know if the smoking habits affected the outcome. Okay, so you can think randomized block design is when we know something about our subjects ahead of time and we're worried about it affecting the results. We can block on that variable, whatever it is, smoking habits, gender, age, whatever. and split our subjects into two groups, and then run two simultaneous experiments where the smokers each get divided into two treatment groups, and so do the non-smokers. And then at the end, we'll be able to compare, how did the treatments affect people that smoke, and how does it affect people that don't smoke? The third method is called a matched pairs design. And a matched pairs design is a special case of a randomized block design, the one number 2. It can be used when the experiment has only two treatment conditions, okay? And subjects can be grouped into pairs based on some blocking variable. Then within each pair, subjects are randomly assigned to different treatments. Okay, so one way to think of this is that you could match subjects into similar pairs, randomly assigning treatments to each pair. You could think like having two identical twins, okay? They'd have, grew up in the same households, they'd have basically the same medical history in their families, et cetera, and then you could basically flip a coin and decide that one of the pair gets, treatment 1, and one of the pair gets treatment 2. If you didn't have identical twins, you could give out all your subjects surveys and decide on a couple of things that you think are important, like maybe exercise level, overall health, medical history, whatever, but you'd pair up two people with similar answers to their surveys, and then give one person one treatment and the other treatment. You'd still randomly decide who gets what, though, so you'd flip a coin or do something like that. Another form of matched pairs is you versus yourself, where we're going to measure a variable for you and then apply some treatment and then remeasure the variable for you. So it's kind of a before and after situation. A lot of times, like alcohol studies are this way, where they have you do something before you drink alcohol and then do some kind of reaction test or memory test or something, and then have you drink some alcohol and then retest you. So it's a you versus yourself situation. That is also considered a matched pairs design. Now, in any experiment, we are hoping to find a difference between our treatment groups. Okay? We hope one medicine heals people faster or makes your headache go away quicker. We hope we find growing conditions that allow our plants to grow a little faster, etc. We hope that we find what we call statistical significance in our results. So, statistical significance is finding a difference between our experimental groups that is so large it can be attributed to the treatment they received and not just by chance variation or chance luck. Okay. Now, when someone asks you if a certain coin is fair when flipped, or suppose someone asks you if a certain coin is fair when it's flipped, meaning it comes up heads and tails at an equal rate. You decide to perform an experiment by flipping the coin 20 times and analyzing the results. Statistical significance results would mean that we find the coin to be not fair, okay? That we actually have enough evidence in our results to prove the coin isn't fair. So, you can picture this. You're going to flip a coin 20 times and see what you get. Now, obviously, if you get 10 each, that is not evidence that the coin is unfair. That'd be evidence the coin is fair, okay? So we'd say our results are not statistically significant, okay? Like what was supposed to happen, happened. But let's say you got 11 heads and 9 tails. Well, that's only one more head than we were supposed to get. That could easily happen just by luck. So we would have to say the coin is fair. Let's say you got 12 heads and 8 tails. Well, that's still only 2 more heads in 20 flips. Okay, that still could be luck. We'd still have to say the coin is fair. Those results are not statistically significant. And then, how about 3 more heads out of 20 flips? That still is not very crazy. That could totally happen. If you think I'm lying, flip a coin 20 times and see what you get. Okay? But at some point, the results will get too crazy, perhaps, and at some point we'd start to believe that, wait a second, maybe this coin is not fair. Now, it may happen before this point, but let's say you flip the coin 20 times and you got 19 heads and 1 tails. Well, this is too far from what we would expect to happen if the coin was fair. If the coin was fair, it would be unreasonable to get these results. Okay? It would take you a really long time to flip a fair coin and get 19 heads and 1 tail. This becomes evidence that the coin is not fair. We would call these results statistically significant. Okay? The early results in this coin flipping study could have happened by chance luck associated with flipping a coin repeatedly. Those results would not be considered statistically significant. Okay, so what we're hoping is, at the end of an experiment, we hope to find differences between our treatment groups that are so large that we can't attribute them to just random chance. But they might be attributed to the treatment themselves, or they must be attributed to the treatment themselves. We then call the results statistically significant.